Hello. So in this part of the video, we will work on relative motion and absolute motion analysis for acceleration calculation of rigid bodies. So we have this equation for velocity analysis for rigid body in general plane motion. And in the previous video, we have talked about acceleration analysis of rigid body in general plane motion. So for general plane motion, its acceleration value of rigid body depends on the absolute acceleration of one point plus relative acceleration of the body for its rotational motion, which consists of tangential part of the acceleration and normal part of the acceleration. And if you further substitute the equations for uh, tangential and normal parts of accelerations, then you will get the final equation here, which is acceleration of a point on a rigid body in general plane motion is absolute acceleration plus alpha cross rb with respect to a minus omega square rb with respect to a. In this equation, omega is scalar, everything else is vector, so everything else has I and j components into it. So let's apply these equations to problem solving. So this is in class chapter 16, in class exercise 4. We have half solved this problem with instantaneous center of zero velocity concept. So we will now finish this problem and calculate the acceleration values. So I read the problem once again. At the instant zone, NA of the rod has velocity and acceleration shown. Determine the angular acceleration of the rod and acceleration of end B of the rod. So this rod is subjected to velocity and acceleration values as shown in the figure here, which they both are downward. And when it is as a result of this velocity and acceleration, the rod AB is in general plane motion because it rotates and translates, okay, in this way. So we need to calculate the acceleration of B end of the rod and angular velocity of the rod, so and angular acceleration of the rod as well. So in the previous example, we have already calculated angular velocity of the rod using instantaneous center of zero velocity, which is shown in the figure here. Now we need to calculate the angular acceleration of the rod. So we assume right now that angular acceleration is in the same direction of angular velocity. And when we assume that, we are assuming that the velocity, angular velocity increases with respect to time. So this is our angular acceleration, alpha AB. And then we also assume that the acceleration of B end of the rod is also positive. So it's also in the direction of velocity. So this is acceleration of B. This is our assumption that AB goes towards right and alpha AB is counterclockwise. We start with this assumption. For this example, our coordinate system, I'm just drawing it here. So our X is horizontal, Y is vertical, and Z axis is perpendicular to this plane of paper, and it's coming out of the screen. This is our assumption. Okay, so once again, I repeat, X is right, Y is up, and Z is perpendicular to this plane of paper, and its positive value is out of the paper, coming out from the paper. Okay. That means counterclockwise angular velocity and counterclockwise angular acceleration, they both have positive unit vector along z direction, because if you use right hand rule and if you bend your fingers counterclockwise, then thumb points up, which is towards positive z. So they both have positive k component of the unit vector. So now end B of this link, so is link AB is in general plane motion, so end B is in pure rotation with respect to A. but then A is also in translation. So the absolute acceleration of NB can be calculated using this equation. So we need to apply this equation to calculate the absolute acceleration of NB. So I'll write that equation here. So AB, now when I draw the arrow on top of the variable, it's a vector, is equal to acceleration of A plus acceleration of B relative to A, which has tangential component. So this is the tangential component of the acceleration, and this is the normal component of the acceleration. And this is our equation 1. Now we need to find out this RB relative to A, alpha, and omega, and substitute everything into equation 1 in terms of I and J, I, J, and K components, and then we need to apply the cross product rule and reduce everything into just I and J components, and then separate all I parts. We get one equation. Separate all J parts or Jth components, and we get the second equation. From those two equations, we can calculate our two unknowns, which are AB and alpha AB. Okay. Now I'm not writing alpha AB every time. I'll just write alpha. That means it's alpha AB if I write it, when I write alpha. Okay. Similarly, when it's omega AB. So I'm not writing omega AB. I just write omega. Okay. So let's find out what is the position. Let's start with alpha. So what is the value of alpha? We don't know its magnitude, so we assume that alpha magnitude is just alpha without arrow, but then its direction is positive k. So this is our equation 2. Okay. For omega, we already have the value of omega, which is 2 radian per second. Okay, this is 3. Now we know the acceleration of A, which is downward, and phi. So acceleration of A is minus phi j. That's equation 4. Then now we need to find out the position vector RB with respect to A. So I draw this small figure here. So B with respect to A is this arrow, where this is B and this is A. Okay, so this is for position vector B with respect to A. So at B it's the head, and at A it's the tail of the arrow. Now based on the given dimensions, we know that this coordinate is 3 in x and 0 in y, and we know that this coordinate is 0 in x and 4 in y. So we can find out the position vector from A to B by subtracting the coordinates of head from tail and just applying respective I and j coordinates to it. So this position vector is 3i minus 4j. Okay, and that's our equation 5. Okay, so now the next step is we need to substitute equation 2, 3, 4, 5 into equation 1. Okay, so substituting 2, 3, 4, and 5 into 1. When we do that, oh, by the way, we don't know the acceleration of B as well, so I need to substitute this as well. So acceleration of B is its magnitude, and direction is towards positive I. Okay, so this is actually 6. So we need to substitute 2, 3, 4, 5, and 6 into equation 1. So when we do this, let's write how would this big equation look like. So this will be ABI is equal to minus phi j plus alpha k cross 3i minus 4j minus 2 square, which is omega square, and again this unit the position vector 3i minus 4j. Okay. Now next step is we need to reduce this cross product to a single unit vector by applying the cross product rule. So this is k cross I, and k cross I is j, and this is k cross j, and k cross j is minus I. Okay, so let's do this. So it's minus phi j. Now 3 multiplied by alpha, so it's 3 alpha, and then it's k cross I, and k cross I is j, so it's 3 alpha j. Now it's negative sign here, so it's minus. It's 4 multiplied by alpha is 4 alpha, and it's k cross j is minus I, and there is also negative sign here, which is from the position vector, and then there is a negative sign in I, so this becomes positive. So this is 4 alpha I. Minus, this is 4, 2 square is 4, multiplied by 3 is 12 I, and this is 4 multiplied by minus 4, but there is negative sign here. So when we expand this bracket, this negative multiply with this negative will become positive. So this will be 4 into 4, which is 16 G. And that's this equation. Then this is ABI. Now we need to separate this big equation into two separate equations. One from all ith components and second is from jth component. So let me use this this like wavy symbol for I component. So this is I, this is I, and this is also I. Okay. So let's separate I components only. So now it's AB. Now we don't need to write I because we are using only ith component for all the variables. So we can just get rid of I. So now it's 4 alpha minus, always maintain the positive or negative sign, whatever is multiplied with ith component or jth component. So it's minus 12. So this is our equation. We call it 7th because we already have 6 up to 6 equations from the top derivation. And now we need to separate all j components. So I use double line for j. So this is j, this is j, and this is j. And there is no j on the left of the equal to sign. So I'll just put 0. On right side, it's minus phi minus, plus 3 alpha plus 16, and that's equation 8. Okay, now it's very simple. From equation 8, we can get the value of alpha, which is angular acceleration of the link, and then substitute value of alpha in equation 7, and we get the value of AB. So let's do this. So when we calculate alpha from equation 8, we'll get the value of alpha, which will be negative. So it's minus 3.66. This is angular acceleration, so it's radians per second square. And then we substitute this negative number. Now do not change the sign here, leave it as negative, and substitute the negative number in the equation 7th and calculate the value of AB. We get negative 26.66. This is linear acceleration, so it's meters per second square. Okay. So now we get the negative answer for alpha and negative answer for AB. What does it mean? It simply means that our original assumption of alpha going counterclockwise and AB going right is not correct. The actual alpha is going opposite to the angular velocity. That means the angular velocity of the link decreases with time, and AB also goes opposite. That means and B also slows down, or the velocity of B decreases with time. So acceleration B is in this way, going left. That is the correct direction of the acceleration, and correct direction of alpha AB is clockwise, not counterclockwise. Okay. So let's correct our answers, because this is not the end. We shouldn't leave our final answer in this way. So the correct answer is alpha is equal to 3.66 radians per second square. And to avoid any positive negative confusion, I draw the actual direction, which is clockwise. Okay. And AB is 26.66, okay, and meters per second square, and I draw the actual arrow which is going left, okay, and these are our final answers. Okay, that's the end of solution. So please go through one more time through the video if it is not clear, and I'll also upload the solution as PDF on Kodiak. So now we will do the next problem from chapter 16 in class exercise 4, problem number 16.116. I have asked you to do I have asked you to calculate the velocity of point B and point C using instantaneous center of zero velocity in the previous class, and then I hope you should have done that, and if you have done it, you can compare your answers with my answers. So, and I told you that the first part you need to do is you need to calculate the distance from A to B and distance from A to C, and you can do that using law of cosines. So when you apply the law of cosines, you will get the distance from A is instantaneous center, so you will get the distance from A to B is 0.382 meters, and distance from A to C is 0.923 meters, and from that you can calculate the velocity of B. Just multiply that with the omega, and velocity of C, again multiply this distance with omega, and you will get the answers as 1.14 meter per second and 2.76 meters per second respectively. Okay. However, this calculation has nothing to do with acceleration calculation. So this is purely an independent problem for instantaneous center of zero velocity. So let's read the problem now from acceleration perspective and solve it. So the disk has an angular acceleration of 8 radians per second square, which is as shown in the figure going counterclockwise, an angular velocity of 3 radians per second at the instant zone. If it does not sleep at A, determine the acceleration of point B. So we need to calculate the acceleration of point B. Now this wheel rolls without sleeping, so only the center point of the wheel is in pure translation, because center has only horizontal velocity, it does not have any other component of the velocity. So center point of the disk, let's call it O, which has only one component of acceleration, which is going left. Okay, and this component is tangential component of acceleration, because there is no normal component of the acceleration for center O, because it does not have any rotational motion, it's pure translation. While and B is the point on the disk which has both rotation and translation. However, with respect to the center point, B has only rotational component, but then center itself has translation component. So the total acceleration of B can be calculated using acceleration of center plus acceleration of B relative to center. And now this acceleration of B relative to center has normal and tangential components to it, where the normal component of the acceleration will point towards center, as I have shown with the pencil here, and the tangential component of the acceleration will be something like this, tangent to point B and points in the direction of rotation. Okay. So let's apply this this concept of acceleration calculation to calculate the acceleration of point B. However, first we need to calculate the acceleration of point O, center. So the magnitude of this acceleration is alpha multiplied by r, where r is the radius of the disk, and its direction is left. So I'm just calculating the magnitude, so I'm using scalar equation. It's alpha is given as 8, multiplied by r is 0.5. So this is 4 meters per second square going left. This is the horizontal acceleration of point O. If I write this as a scalar, and I define my coordinate system as x going right positive and y going up positive, then this is going left, so it's minus 4i, because I is the unit vector in the direction of x-axis. This is meters per second square. Okay, this is one equation. Now for acceleration of b, I need to apply both the absolute and relative components of acceleration. So acceleration of b is acceleration of o, which is translation, plus acceleration of b relative to o. Okay. So I expand this equation. So this is acceleration of o, and for this part I'll substitute both normal and tangent components of the acceleration. So it is alpha cross rb relative to o, where alpha is vector and this is also vector. So this is tangential component of acceleration, and this minus omega square multiplied by rb, this is normal component of the acceleration. Okay, so this is our standard equation, that acceleration of this point b is acceleration of o plus acceleration of b relative to o, and this is our equation. Let's call this equation 1. For this equation, we need to first of all find out all this acceleration on the right side of, because we are actually calculating the acceleration of b, so we don't need to substitute I and j components of acceleration of b. In fact, when we solve the right hand side of the equation, we will get the I and j components of acceleration of b. So we will leave this as is, and we'll substitute the other vectors in terms of their I and j components. So acceleration of o, we already know it's minus 4i. Now alpha is 8k, because it is counterclockwise and z-axis is perpendicular to the plane of paper, so it's 8k. rb relative to o is, for that I'll just say that if this is point o and this is point b, I'm just redrawing this one more time here, and this angle is 45 degrees, and this is x-axis positive and y positive is up. Okay, so, and this distance OB is 0.5 meters. So 0.5 sine 45 degrees is I component, and that is positive, and 0.5 cosine 45 is j components, but it's negative because it points down. Okay, so RB with respect to O is 0.5 sine 45 I minus 0.5 cosine 45 j, and this is the value of position vector RB relative to O. We know the value of omega. This is scalar, so we don't have to write any I, j or k components for it, so it's just 3 radians per second. Now we can substitute all these values. Let's call this this is 2, because I have already given number 1 here. This equation is, this is 3, this is 4, and this is 5. Substitute 2, 3, 4, 5 into equation 1. So substituting 2, 3, 4, 5 into 1. So let me slide the paper up. So when we do this, we'll get acceleration of B is equal to minus 4i plus 8k cross this curly bracket here. So I'm just, to save space, I'll just write curly bracket. This curly bracket is RB with respect to O, minus 3 square, which is omega square, and once again this curly bracket, and the curly bracket is this whole thing. Okay, and when you expand this using cross product rule, so it's k cross I, and that's j, and it's k cross minus j, which is positive I, and then you do solve this part as well, same as previous example, uh, and you combine all I and j parts, you will get this as minus 4.35 I plus 6.01 j, and that's the acceleration of point B. Okay, so this is the acceleration of B, which has negative I and positive j components into it. We have been asked to calculate the magnitude and direction of acceleration. So the next step is, because this is a vector with I and j components, you know how to calculate the magnitude of the vector, which is square root of I part square plus j part square. Okay, and if you do that, you'll get this number as 7.42 meters per second square. Okay. And then angle theta is 10 inverse of 6.01 to 4.35, and when you do this, you'll get 54.08 degrees angle. Okay. And these are our final answers. So yeah, once again, go through the solution. You can replay the video if it's not clear, and the solution is also on Kodiak. So practice these two examples, and it's more about understanding the concept. So try to understand the concept that when a rigid body is in general plane motion, then it has both absolute component of acceleration and relative component of acceleration. And relative component of acceleration, if it is because of rotational motion, then it will have tangential part and normal part. Okay, be careful with the sign convention for position vector, and also when you apply cross product and reduce everything into I and j components. This is one of the problems where you need to spend more time in exam to solve it, and I suggest you double check your answers at the end if you have time.